Hi, Ms. Barber here. This lesson is titled Laws of Logarithms. In this lesson, we will learn some properties of logarithms. These properties give logarithmic functions a wide range of applications. So, the learning objectives of this lesson are: 1. Know the laws of logarithms. 2. Be able to expand logarithmic expressions. 3. Be able to combine logarithmic expressions. And 4. Be able to use the change of base formula to solve logarithmic applications. Roman numeral 1. Laws of logarithms. Since logarithms are exponents, the laws of exponents give rise to the laws of logarithms. Let a be a positive number with a not equal to 1. Let capital A, capital B, and capital C be any real numbers with capital A greater than 0 and capital B greater than 0. 1. Log base A of AB is equal to log base A of A plus log base A of B. That is, the logarithm of a product of numbers is the sum of the logarithm of numbers. 2. Log base A of the quantity A divided by B is equal to log base A of A minus log base A of B. That is, the logarithm of a quotient of numbers is the difference of the logarithm of numbers. And 3. Log base A of A to the power of C is equal to C times log base A of A. That is, the logarithm of a power of a number is the exponent times the logarithm of that number. Evaluate each expression. A. Log base 6 of 9 plus log base 6 of 24. Let's use the properties of logs and re-express this expression as log base 6 of 9 times 24. That would be equal to log base 6 of 9 times 24 is 216. We can continue to simplify and write this as log base 6 of, and 216 is actually 6 to the power of 3. And using identity properties of logs, log base A of A to x is x, so log base 6 of 6 to 3 is 3. Let's do B. Log base 2 of 8 to the 15. We will write this as log base 2 of 8 can be written as a base of 2 raised to the power of 3, and we still have to the power of 15. Using properties of exponents, we can express 2 cubed to the 15 as 2 to the 45, and then using the identity property of logs, we get that this is equal to 45. Let's continue to part C. We'll begin by saying that log base 5 of 1 over the square root of 125 is equal to 125 to the negative. We're going to move the denominator to the numerator, and the square root is 1/2. Then we have log base 5 of, we will re-express 125 as 5 cubed to the negative 1/2. Let's use properties of exponents, and we'll write this as log base 5 of 5, and then to the power of, you multiply the 3 and negative 1/2 together, which would give you negative 3/2. And the identity property of logs gives us that this is equal to negative 3/2. Roman numeral 2. Expanding and combining logarithmic functions. The process of writing the logarithm of a product or a quotient as the sum or difference of logarithms is called expanding a logarithmic expression. The process of writing sums and differences of logarithms as a single logarithm is called combining logarithmic expressions. Note, although the laws of logarithms tell us how to compute the logarithm of a product or a quotient, there is no corresponding rule for the logarithm of a sum or a difference. Use the laws of logs to expand each expression. Part A, the natural log of the quantity x to the fourth times y divided by 3. I'll begin this expansion by using the second law of logs and expressing this quotient as a difference of logs. So I'll write this as the natural log of x to the fourth y minus the natural log of 3. Now, let's use the first property on the first term and write the natural log of x to the fourth times y as a sum of two different logs. So that'll be the natural log of x to the fourth plus the natural log of y minus the natural log of 3. And then we have one more algebra to complete in order for this to be fully expanded, and that is to move the power of 4 in the first natural logarithm to the coefficient. So this will be 4 times the natural log of x plus the natural log of y minus the natural log of 3. Part B. The common log of the square root of x times the square root of y times the square root of z, all nested. I will do this problem using parentheses rule from outside in. So the first step would be to re-express this as the log of, and where I have the square root of x, I'll rewrite that as x to the power of 1/2. And it is still multiplied to the square root of y, and within it is multiplied to the square root of z. Let's use the property that lets us write the exponent as a coefficient. So this will become 1/2 times the log of the quantity x times the square root of y times the square root of z. Let's expand the term within the parentheses using the first property or the first law of logs and write that product as a sum. So this will become 1/2 times the log, and then here we're going to write this of x plus the log, the natural log, the square root of y times the square root of the square root of z. Let's do the similar thing to the second term, which is log of the square root of y times the square root of z. So this would become 1/2, be very careful with the parentheses, log x of, and then bring the 1/2 for the square root of y as a coefficient. So we'll write this as 1/2 the log of, and now we'll have y times the square root of z. Let's continue to expand. So this will now become 1/2 log x plus, then we'll have 1/2 of log y plus, and then we'll go ahead and rewrite the square root of z as z to the 1/2 and express it as a coefficient. So you have 1/2 of log z. Now let's take care of all of the 1/2s and multiply it through. So this becomes 1/2 log x plus 1/4 of log y plus 1/2 log z, and then let's expand the 1/4 to rest of the terms. So we would get 1/2 log x plus 1/4 log y. 1/4 times 1/2 would be 1/8 log z. Use the laws of logs to combine the expressions. A, 1/2 log base 2 of 5 minus 2 times log base 2 of 7. The first step is to rewrite the coefficients as an exponent, so we begin by rewriting the first term as log base 2, 5 to the 1/2, And then going to the second term, we'll do minus, and we'll rewrite this as log base 2 of 7 squared. We move the exponents to the powers. Let's write this again, changing the power of 1/2 to the square root notation. So this would be log, the first term would be log base 2 of the square root of 5 minus log base 2 of 7 squared. Now we can use the difference to quotient law of the properties of logs and express this as log base 2 of the quantity square root of 5 divided by 49. Part B. 2 times the quantity log base 5 of x plus 2 times log base 5 of y minus 3 times log base 5 of z. We work from the inside out, so in the first step, we would have 2 times log base 5 of x, and for the second term where the coefficient is 2, we rewrite it to make it the exponent of y, so this will be plus log base 5 of y squared. Similarly, for the third one, we rewrite the coefficient of 3 as a power for the z, so the 3 times log base 5 of z becomes the expression log base 5 of z cubed. Now, let's use the properties that let us combine the sum of 2 logs as a log of a product. So this becomes 2 times log base 5 of x times y squared, and this will be divided by what is subtracted, which was log base 5 of z cubed, so it'll just be divided by z cubed. Let's continue. We will now move the coefficient of 2 in front of the entire logarithm to the power of that expression, so it'll be log base 5 of the quantity x y squared over z cubed, and all of that is squared. And now we use laws of exponents and express this as log base 5 of, and we're going to square x times y squared over z cubed, and that will give you x squared. Y squared squared is y to the 4th, and z cubed squared is z to the 6th. Roman numeral 3, the change of base formula. The change of base formula is given by log base b of x is equal to log base a of x divided by log base a of b. When computing applications, use either the natural log or the common log, as both are standard in scientific and graphing calculators. Use the change of base formula with an appropriate base to simplify log base 8 of 16. Let's recall the change of base formula says if you have log base a of x, it is equal to, pick a different base, log base b of x divided by log base b of a. I see the base 8 and know that that's a number with a base of 2, and same thing with the 16. So I'm going to choose base 2 as the rewriting change of base formula, and I'll write log base 8 of 16 is log base 2 of 16 divided by log base 2 of 8. That's an application of the change of base formula. Now let's use some properties of exponents. This will be log base 2, and 16 is 2 to the 4th divided by log base 2. 8 is 2 cubed. Using the identity properties of logarithms, if the base of the log and the base of the exponent are the same, then it simplifies to just the exponent. So the numerator for log base 2 of 2 to the 4th is 4. And for the denominator, log base 2 of 2 cubed is 3. Log base 8 of 16 is exactly 4/3. Use the change of base formula and a calculator to compute log base 12 of 2.5 accurate to 5 decimal places. When using the change of base formula and a calculator, the wise choices for the common base is either the natural log or the common log. Either way, we would write log base 12 of 2.5 is the natural log of 2.5 divided by the natural log of 12. And if we use the common log, then we would write this as log base 12 of 2.5 is equal to the log of 2.5, that's understood to be base 10, divided by log of 12. Now let's compute this using a calculator. What I have displayed is a TI-84 Plus CE calculator screen. Let's compute the natural log portion first, and to do so, let's locate the natural log button on your calculator as the natural log of 2.5, and then hit the divide symbol, hit the natural log of, and the base was 12, close and enter. Now let's see what happens if we use the common log. So we'll do log of 2.5, close that, and then divide that by the log of 12, close, enter. Let's observe that we got exactly the same value whether we used a natural log or the common log. So the answer accurate to 5 decimal places is 0.3687. The digit following 4 is 2, so it does not round up.